Last time you ran the forward pass and cached every number on the way through. Z1 equals 080, A1 equals 080, the prediction 0.6398, and the loss 0.247. That cache wasn't bookkeeping for its own sake. It's fuel. Every value you stored is something the backward pass is about to consume. So here's the thing, nobody tells you cleanly. Backprop isn't a separate algorithm bolted onto your network. It's the same graph walked in reverse, multiplying one tiny local derivative at each step. By the end, you'll watch a single number, the loss, flow backward and split itself across all four parameters, and the gradient norm land on 0.31. Start with the misconception that trips up almost everyone. People think Backprop computes the gradient as one big mysterious formula. It doesn't. It computes one derivative, dl dy, and then it does nothing but multiply. Every other gradient in the net is that first number carried backward through a chain of small local multiplications. Our loss is half of y minus 0 squared. Differentiate that and you get y minus the target, 0.6398. One number, that's the entire seed. Everything downstream is just that. Seed times a sequence of local slopes. Here's the second myth, that the chain rule is something exotic. It's the most boring multiplication you've ever done. dl dz2 is dl di times di dz2. Our output went through a sigmoid, and a sigmoid slope is beautifully cheap. By times 1 minus I, that's 0.2305. So del dz2 is 0.6398 times 0.2305, which is 0.1475. And notice why we cached the output and not the input. The slope is written in terms of y, the number already on the shelf. Now watch the weight gradient appear and notice it costs you nothing new. dl ww2 is dl diz2 times w2. And diz2 w2 is just a1, the activation you already cached on the way forward. You don't recompute a1, you read it. So w2 is 0.1475 times 0.d, which is 0.80. A weight's gradient is simply its incoming activation times the error flowing back into it. Nothing more. The bias is even sneakier in how simple it is. dl db2 is dl dz2 times dz2 db2, and dz2 db2 is 1, because the bias just adds. So db2 equals the error exactly, 0.475. A common wrong intuition is that bias gradients are some separate species. They're not. A bias is a weight whose input is permanently pinned at 1. Its gradient is just the error, undiluted. Now we cross the ReLU, and here's where a whole future episode hides. To push error from the activation A1 back to the pre-activation Z1, you multiply by ReLU's local slope, which is dead simple, 1 if the gate was open, 0 if it was shut. Our gate was open, Z1 was 0.80, safely positive, so the gradient passes straight through unchanged. But hold on to that 0 case. A unit whose gate is shut gets no gradient at all, it can't learn. That's the dead ReLU trap, and it's the first cousin of the vanishing gradient story we hit later. For now the gate is open, so the error sails through. One rule that makes the graph branch: when error flows back into the hidden layer, it doesn't go to one place. It fans toward W2's gradient and keeps flowing toward W1. At a node where the forward pass added, the backward pass copies the gradient to each input. At a node where it multiplied, the backward pass swaps in the other factor. Add copies, multiply swaps. Those two rules plus the chain are the entire backward pass. There is no third rule, so assemble it. dl day1 is w2 times dl dz2, the error projected back through the very weight it went forward through, which is 1.5 times 0.10475 or 0.2212. Then dl dz1 multiplies in the ReLU gate, still 0.2212 because the gate is open. Then dl dw1 is dl dz1 times the input x, 0.2212 times 0.50, which is 0.1106. Every edge on the reversed graph carries a number, and every number is a literal product of two things you already know. No magic, just multiplication walked backward. Open 04 backward sweep.py. It's the mirror of last episode's forward file. Forward built a set of cached values going down. This file walks them in reverse, and at each node applies exactly one local derivative rule. We finish by flattening all 4 gradients into one vector and taking its norm, and we'll check it against a brute force finite difference gradient, so you believe the chain rule actually gave the right answer. First, the cached forward values, copied verbatim from OPO3 so the 2 episodes line up, the input X, the weights, and crucially the cached Z1, A1, and Y. We don't recompute them. The backward pass is a consumer of this cache. This is the whole memory versus compute trade-off of backprop in 3 lines. The seed, D heart, do I heart, E star, 1 subtraction. This is del die and it prints 0.6398. Everything else in the file is this number being multiplied by local slopes. If this line is wrong, all 4 gradients are wrong. So it gets its own line and its own print. The output layer walked back. JZ2, D hat E hat 1 dihatum, the sigmoid slope 0.2305, giving DZ2 of 0.1475. Then W2 or DZ2A1 and DB2 or DZ2. Notice W2 uses A1 straight from the cache. The forward activation is the local derivative DZ2W2. 3 lines, 2 of the 4 gradients done, 0 new forward work. Crossing the ReLU, day 1, W2 DZ2 projects the error, back through the output weight, then dead Z1 of day 1, Z1 on 0, multiplies in the gate bit you cached. The gate was opened, so DZ1 is 0.2212. That one multiplied by 0 or 1 is what kills a dead unit's gradient. It's the line that generalized to many layers either preserves or destroys learning. The first layer, W1, DZ1X and DB1, Z1. Error out times input in for the weight. The bias input is implicitly 1, so DB1 is DZ1 copied through. Same 2 rules as the output layer, 1 layer earlier. The norm and the check. We concatenate all 4 gradients and take neb.linalg.norm. That's the 0.31 headline. Then finite diff nudges each parameter by 1 in E5, reruns the forward, and measures the loss change numerically. The max absolute difference between analytic and numerical is 7.0E08. Floating point noise. That tiny number is your proof the backward graph is correct. So that's backprop. 1 cached forward pass, 1 reversed sweep. Every gradient a product of local slopes you already stored, and a norm of 0.31 you can verify to 8 decimal places. But here's the question that should bug you. We walked the graph backward to get all 4 gradients in one pass. Why backward? Why not forward? Next episode, why reverse mode is the cheap one, and the exact crossover where forward mode would actually win.